So Stephen, after your talk, I'll take you down to my paleontology lab.
Sounds good.
I've got a few minutes before my lab starts. I'll show you around.
Sure.
We have an alum who has been very generous to give us some nice things over the years.
Relevance.
Oh, yeah. Did you
Well,
see the
but
drum?
they're-
I did. It is.
Wait 4 more days.
Just one more time to make sure that we are live. Just in time.
Without getting it all over.
Trying to run like Zoom to a live YouTube stream.
Yeah.
To split screen.
You're a master, Rob.
Well, this is taking practice to get here. Remember last week I was having you help with that just so that I can run it. This is a little bit nicer.
I left all your notes in here yesterday. And there was still a lot of people. I got it. It's like. This is what's gonna stay down forever. But they were really so short, even like. Up there.
So we have to tell.
Yeah.
Sign it.
And-
Sign it.
Sure.
Sign. Every other week.
Yeah.
Disaster.
So-
Same
To-
Okay, all the states. But it's share with environmental history. It's good variety.
Hey, gentlemen.
You.
Paleontology this semester, as well as a first year seminar on natural disasters.
Okay.
If I put my hands in there, I could get.
Yeah.
I'll be ready.
That makes sense.
Oh, my.
I can understand that.
No.
It's for my perspective. It would be my main attractant.
Here comes my colleague Ben Edwards. He's a volcanologist, and Ali Thibodeau's a geochemist. Knowles retired. Ben, Alec, Stephen Jasinski from Harrisburg University. Ben Edwards, Ali Thibodeau.
As you tell.
She's our department chair. She runs the place.
So that's, you guys have a GIS program?
We do.
Yeah, I think I know the guy that runs the GIS program.
Yes. Albert Sarvis.
Yeah. I do drone stuff too. So
Okay.
he's like spun off his own company, I think, to do drone stuff.
Oh, really? Wouldn't surprise me.
Yeah.
Mike Myers doing a lot of drone stuff then as well. So,
Wow,
yes.
very good.
Hmm?
Yeah, very cool.
All right, we need to get started.
Okay.
All right, welcome to this week's Earth Sciences Lunch and Learn seminar. Next Tuesday, we do not have a seminar speaker. But you'll be getting advertisements from Deb on upcoming seminars. Our speaker this week is Stephen Jasinski from Harrisburg University, Department of Environmental Sciences. Stephen got his undergraduate degree in geobiology at Penn State University, then went on to University of Pennsylvania for his PhD. And now he's a professor of environmental sciences, and he'll be telling us about his recent work in the San Juan Basin and what it means for late Cretaceous dinosaurs and ecosystems in the southern United States. Let's welcome Stephen.
Thank you. So we'll go through this. There's a lot of pretty pictures and things like that, and we'll explain things as we go, but presumably that will allow things to be a little bit easier to understand. We're not going to get into a lot of hardcore geology, but we will touch on things like stratigraphy to get a better idea. So what I've basically done now for longer than I oftentimes care to realize is that I've been continuing field work that had been started before me in the San Juan Basin, which is heavily concentrated in New Mexico, right? So if we look at the United States, even though we're focusing over here, where we're at, we don't want to focus on that right now, right? We're moving over to the Western US. We're looking at those Rocky Mountains. What we're really focusing is a portion of that known as the San Juan Basin. When we look at the San Juan Basin, while it is in southern Colorado and New Mexico, the part I tend to focus on is the New Mexican part. It's a lot better as far as looking at strata, rocks that contain the right age that we're looking for, late Cretaceous into the Paleogene. But what I really focus on mostly is that late Cretaceous time where we still have dinosaurs available and present, right? You can see the gray area showing you Cretaceous outcroppings with a lot of the Paleogene and Paleocene stuff kind of over in this area. So we focus on that, right? We're focusing in on the Mesozoic. We focus in further. And within the Mesozoic, we're looking at, right, Triassic, Jurassic, Cretaceous. And even though we have Triassic material close to where we are at now, we don't have a lot of good dinosaur material here. In the eastern portion of the US and Pennsylvania, we don't have almost any Jurassic over here. As we move west, we get a lot more of that. But what we're focusing, of course, is on the Cretaceous, and we're focusing on mainly these areas up here, these last two periods, the Campanian and the Maastrichtian, which is where we have good information for dinosaurs in the San Juan Basin in New Mexico. All right, so if we look at how the world's looking through time, we focus in on the way things were at the beginning of the Cretaceous here, about 140 million years ago. You'll see that it looks pretty similar, although the oceans are a lot higher, so a lot of the western coast is underwater. But we don't have a lot of good areas for fossils in a large portion of the US for that, or even in North America. So as we move through time, you'll see things changing, right? We move into kind of the middle Cretaceous. We get that western interior seaway starting to open up throughout the western portion of the country. This is where we're starting to get a lot more of a fossil record. We move further through time, we get in towards the late Cretaceous. Now we're getting a lot better. You can see the Rocky Mountains over here having already formed, and we are kind of right on the eastern edge of these. Here is New Mexico, so currently it is still underwater. We move forward again, we're getting closer to Late Cretaceous. We're now in the Campanian. Now all of a sudden you have this on dry land right on the western coast of that western interior seaway. And as we move to the end of the Cretaceous, now that seaway is really, really significantly receding. Things are becoming a lot drier. So we don't have nearly as good a fossil record in most places. But we do have that present still in the San Juan Basin where a lot of this work is being done. So again, when we're looking at the San Juan Basin, we're looking at badlands, looking at a lot of things like this. You get this being a little bit higher up within the actual strata. We have a lot of what's called the Kirtland Formation here, Lake Campanian. You move up to just barely above this kind of concretionary layer. We get into this very small layer that we call the Maastrichtian at the very, very end of the Cretaceous. And then at the very, very top of this, we have some Paleocene strata right after the time when dinosaurs went extinct. So what we're really looking at here, when we focus in, is that we're focusing in on what's called the Fruitland and Kirtland formations, that green stuff signifying the Cretaceous. We have a little bit of what's called the Nahashobito member right at the very end of the Cretaceous, and it's kind of in this little small layer here. So there's not much strata for that, but we still at least get a little bit of it. So if we jump back and look at how we understand dinosaurs at this period in time from this area, we focus in on some of the earliest work being done in the early 19th century, or in the beginning of the 20th century, so the early 1900s. And you get things like the American Museum of Natural History started out there briefly for basically 2 field seasons with Barnum Brown leading a lot of that. Barnum Brown is more famous for discovering and naming T-Rex, but he spent some time here. He's also famous for having a lot of his field crew do most of the work, as many of the early paleontologists, especially vertebrate paleontologists, did, and then posing for pictures in things that make no sense, like these giant fur coats in the middle of the desert. So this was in the middle of summer. Regardless, Barnum Brown was one of the first people to do any work out here, and he discovered and named Cretaceous navajovius. It is a sauropelophyne hadrosaurid, one of the duck-billed dinosaurs. You get an idea what it looked like here. A very, very nice skull. But basically all they did was they went out there, they looked really quick for anything that was basically on the surface, and then they left. And so this is really all that basically became of that. So they didn't spend a lot of time out there and do much work. You had the US National Museum, the Smithsonian, go out there briefly afterwards, and they discovered things. Charles Gilmore helped name Alamosaurus, a sauropod, a very important sauropod at the end of the Cretaceous, because basically it seemingly for a long time was the only sauropod we thought was around. It's still the only one named from the Late Cretaceous in North America. There's suggestions that there's more than one type based off of not a lot of material. But again, even with this, you get an idea of the size of this animal, bones like scapula and pubis here, not a lot of material, but we still know gigantic sauropod. We move into kind of the end of this early time, and we get the famous collector Charles Sternberg, who worked mostly in the early 1920s here, but he was an independent collector, so he sold the things he collected to various museums, including places like the American Museum of Natural History in New York, the Uppsala Museum, or the Uppsala University Museum of Evolution, Field Museum of Chicago, and the San Diego Museum of Natural History. So all of them got portions of what he collected.
Stephen, what do you think about those kinds of for-profit amateur collectors?
So what I would say, of course, is I would like specimens to go into institutions so they can be studied. Now, if they're for profit and the profit is still trying to determine, he basically tried to make sure he got everything to a museum of some sort, even though he sent them to all kinds of museums. But he collected good information with everything he had. And so there was a lot of good stratigraphic information, locality information, which is necessary for all the fossils that are being collected anyway. So if you're trying to get to an actual museum, then I don't have nearly as much of an issue with it. If you're just selling it just to make profit to private individuals, which oftentimes does happen, especially out west on private ranches and things, then that's unfortunate because a lot of things get lost, right? There is talk about, there's the famous Pachycephalosaurid Draco Rex, which is potentially a juvenile Digimoloch and potentially a juvenile Pachycephalosaurus. But right, it was named Draco Rex after dragons, Hogwartsia after Hogwarts. And basically, it's the only specimen I have heard. There are up to 24 other specimens, and they are all in private hands. I know of an individual who went to a person's barn and saw at least half a dozen perfect skulls of this dinosaur that they are currently trying to sell for profit to various places. But scientists can't get in to study them or know anything about them because it's all private material. So again, having lots more people looking for things is a really, really good idea, but I don't like the idea of them kind of getting lost and then losing that information. Because even if you collect something and you don't collect any information with it, the specimen itself is not that useful to actually have. So that's what I would say. But we do have good information for what he was doing out there as well. There's a lot of information, both in photographs from him actually doing work in the field, but also us relocating a lot of his old quarries to figure out what he was collecting, where he was collecting things from. And so here you have one that ends up being this as the sketch in the field was made. So this is the first major skull of Pentaceratops, is eventually named for him. This was one of the specimens he sold to Sweden, in the Uppsala University Museum. And then Carl Weimann worked on most of this material. So one of the major aspects that we have for that, he also sold other things to Sweden, such as this is a partial crest right here, right, of Parasaurolophus tubicin. The southern ones, Harrisburg walkeri is the famous one from Alberta and Canada and things like that. But this wasn't the only type of hadrosaur, Landeosaur he found. He also found a different species of Parasaurolophus, Late. This one he sold to the Field Museum in Chicago, which was eventually worked on by John Ostrom, who is famous for dinosaur paleontology, for discovering Deinonychus and raptors, dromaeosaurs, and a lot of things like that. But regardless, this was kind of the major early part of what we were looking at when we were looking at a lot of these early discoveries for what they had. Mostly single specimens that would kind of get collected and then put in other places. Now you jump forward, right? Basically 70 years before then actual field collecting happens on a more significant basis more quickly. And this is where Robert Sullivan, who had gone to the University of New Mexico for his undergraduate degree, went back to the San Juan Basin, New Mexico, after he took over the State Museum of Pennsylvania for further field work. So he did it on a more significant, consistent basis, starting in the mid-90s. And the New Mexico Museum of Natural History and Science kind of sporadically went out every so often, mostly with basically a private researcher who just liked to look for things. That's Paul Seeley. He tended to focus on ammonite research, but he would just collect anything he could find anywhere. And you'll see the significance of his name then as we move forward with some of these other things. But basically, as we move through now, I'll show you some field images, just looking at kind of what we're looking at, where we are at. When we're looking at these, remember I mentioned the Fruitland and the Kirtland formations as some of the major ones. Those are campaigning in age. The Fruitland is older. It also ends up being more of a brownish coloration as far as what you're looking at stratigraphy wise. And we get a lot of various things. Here's a theropod pubis. Most of the time, you're looking at floodplain deposits. Therefore, we're looking at isolated elements. We very, very rarely find more than one single bone in any one spot. This is not like we're finding complete skeletons. You're mostly finding isolated things. And oftentimes, you're finding them like this, where they've already been weathering for a while. They've partially been breaking down. And so they might also be complete not only prior to burial, but also afterwards if we can't find them soon enough. So sometimes you get things like this, does not look like much of anything. You may be able to see some discoloration as far as browner material. That browner material is bone. This ends up being a partial skeleton that was collected over several field seasons of an ankylosaur. This was eventually named Ashish Lapelta by one of the alums of Dickinson, Mike Burns. So he worked on this after it was collected, I believe, over about 5 total field seasons. This is some of the later material that was collected, mostly osteoderms, bones within the skin of these armored dinosaurs. But there is other bones as well from it. We also are unable to have anything with wheels or gears or motors out there at all because it is considered a wilderness area. So all material has to be lugged in and out by hand. So normally when we get big things, we carry them out on stretchers or in large nets, things like that. If you get something gigantic and you can convince them to do it, you can get things like the Army Reserves to airlift things out via helicopter. That's happened a few times, not often. Most of the time, it's just you walking miles and miles, carrying things in and out. So sometimes you do get articulated things. This might not look like much. It is weathered, but it is a string of caudal vertebrae, probably from a ceratopsid, from lower in the section. As we go through, sometimes things are a little more brightly colored. This is a caudal vertebra from probably a hadrosaur, but you can see that the orange coloration clearly makes it stand out a lot easier than some of these other things. Here is part of a nasal from a ceratopsid. The nasal horn would be right here if it was preserved, but this ends up being part of cavity, the side, front of the face that you're looking at for these horned dinosaurs. And we keep going. This is a little dark. or at least a little light, not dark enough, you might be able to see the bone starting right here. It's part of the ilium, so part of the hips. Here it's a lot more clear of the hadrosaur that has been collected. Things like the lower jaw here after it's been partially basically coated in a material that allows it to be strengthened. It shows up a little bit easier. So this is what the lower jaw would be.
What do you squirt in there? Is that super glue?
It's mostly PVA, so polyvinyl acetate. It's always some kind of polymer that you're using that's supposed to seep through the holes, right? The pores of these bones that allows them to become stronger as you go through time. Now, if you do that too much, you can't get rid of it, and you can lead to issues when trying to fully prepare out the bones afterwards when you get them back. But while you're actually doing that, at least in the field, sometimes if these are already breaking down, which oftentimes they are, that's the only way to ensure that you maintain that original shape and can then work on them afterwards. So sometimes you get larger things that you have the same kind of idea with. Here we have a tibia for a hadrosaur, so just part of the lower leg of one of these dinosaurs. And you can see after you kind of start really getting rid of a lot of that matrix, the bone around it, kind of what you end up getting thereafter. So again, as we move up in section, rather than having more of that brownish, yellowish type coloration we're getting for the strata, we get more of this gray patterning in the upper Kirtland formation. So we're becoming younger as we go through time. And sometimes you'll get a lot of banding of these purples and grays and things like that as we go. This is all that Kirtland formation. You'll see at the very, very top, it changes. That ends up being that slight Maastrichtian and Paleocene layer as we get up to the very end of the Cretaceous.
Are those purple horizons paleosols?
Yes, they are.
Wow, there are a lot of them.
Yes. And certain areas, they are far more significant and common than others. So even when we're up in that upper Kirtland area, they're not consistent necessarily, but certain areas they really come through. So as we move that in the Maastrichtian, the very end, we don't have a lot of material. You're basically looking at a few meters, whereas oftentimes you're looking at tens or hundreds of meters of overall strata when you're lower. Up here, you'll get almost nothing. So the material we have is highly less common. There's also less area to look in, and it's oftentimes less consolidated, which means it's not preserved as well. So here you'll see a slight bone sticking out. What it ends up being here, it's a little bit easier to see, is part of the ilium of an ankylosaur, an as yet undescribed ankylosaur that's close to something like those from Alberta, but we don't have enough material from it. We have things from that back hip area, and we have part of things like vertebrae and ribs that are still articulated, they're together, still looking for more of this kind of thing. So we also, again, have discovered more of that sauropod Alamosaurus. Things like this is part of a pubis down here. This is oftentimes what you're looking at. We are very high in the section, and sometimes you get material that is a little bit easier to get through, sometimes not. Here it's a little bit easier to see as it's coming out a little bit more. It has been coated in that protective coating to kind of help it out a little bit. We also have other things that are not just bones that help us determine what's happening. Things that kind of were ignored early on. So things like footprints, right? This ends up being a very, very large hadrosaur, but ichnology, the study of trace fossils and footprints and things can be difficult because you have to think of the sediment and things that they're walking through as far as how that's going to change things. So even though this foot looks gigantic, the foot itself is probably a lot smaller, right? And as it pushes through that sediment, it changes the shape a bit as you go. Either way, a very large animal. We have some plant material. There's an area out there called fossil forest because of all of the fossilized trunks and stumps and things like that that are present. We can't get as much information about what they were. It's more generalities, but sometimes you get them sticking out like they legitimately just look like a normal tree that has just been cut down. You also get logs then that are still being maintained in a lot of shapes. They are a lot more common. Fossilized wood in some form is very common as you're walking through. And you can see how these kind of stick out then as you're looking with some bones, of course, still actual bones present around them, right? So we don't have as much information on the plant life as we would like, but we still at least get some of it. And we get some things that are a little bit less common. This ends up being basically the bulb of a palm of some sort. We still don't know any more information other than it is a root bulb for a palm at the moment. So we're still looking into a lot of things. But we do get some actual quarries, or at least things that can be quarries, and sometimes where we get a lot more material. So here we have an area, again, it's much lower because it's that yellowish brownish color. And you may be able to see several bones within this. We highlight them. I can show you a little bit better. So this ends up being an area where this is a partial hadrosaur skeleton with lots of elements. Unfortunately, because there's nothing to look over and double check these things, this is a specimen that has been at least partially poached and taken away now. There's lots of reasons for that. Part of that is that someone was brought on to be a field hand and to help. And after they no longer were working with the scientists, they came back out with some friends and decided to try to take the bones out for themselves. So unfortunately, that can happen. One of the reasons we try to be a little bit careful with the people we bring out to help out, and hopefully all those people understand that these are important to be maintained as far as these kind of things and not essentially be ruined. Because what we end up finding out is that while some of them were taken out correctly because they were just gone, a lot of them, because the people who tried to do it didn't really know what they were doing, also basically just destroyed them and then left them there. Because they tried to get them out, they couldn't, they broke down, they fell apart, they got destroyed, and then they left.
You have to have a permit from the government to do this?
You do, but I will simply say that because you're basically out in the middle of nowhere, there's no real way, unless someone randomly is walking out there and asks to see your permit, there's no real indication or way for them to stop someone from just driving out there and doing something. So while they do have people, and this is land all covered by the BLM, the Bureau of Land Management, the basics are that they don't have enough people to police anything, basically. So unless they're given a tip or told someone's out there directly, they probably won't be able to do anything. So this was a situation where we basically were able to backtrack easily and figure out how they were already connected. Otherwise, if it's some random person, we would have had no idea. So we are getting some other new things that we actually are able to collect. Here you can at least see some bones. Here you can already see some that have been taken out. And maybe you can see at least a little bit of the outline of what we have as far as multiple sets. This ends up being a partial skull, where we can at least get parts of what ends up being a frill. Part of the maxilla, the upper face, was here before it was taken out. And so this is a ceratopsid dinosaur, another one of the horned dinosaurs. And this is a specimen that has not been prepped out at all, but still at the museum waiting further preparation, things like that. Not going to be a fast process, but eventually we hope to get that moving again and figure out exactly where these things are and what that really means. This ends up being really high in the section. And basically what this ends up being is it's either going to be something new, or it's going to be an important thing that connects what we have here to what's happening in Montana with the issues surrounding Triceratops and Torosaurus. And I won't get into that, but if you understand what that is, you might have an idea then of how this might play into those kind of things. So as we move forward again, right, we've been looking at this significant increase in what's happening in New Mexico since the 90s. Whereas I have been a major part of that kind of collecting idea. And now we'll go through at least one of the big additions that we have simply is the idea of biodiversity. So what are distinct new dinosaurs that have been then collected and described from there, showing us the difference of what's happening basically now versus what we thought we knew before. And some of those are things like ankylosaurids. Might not be easiest to see. You have an eye here. You have the nose coming out here. These are horns coming off kind of the back of this thing's head. So this is Notocephalosaurus. This is one of the earlier ones that was collected when that collecting effort really started back up in the 90s. More recently, now we have more ankylosaur specimens being collected. It's a bit different. Again, you can still see the eye. Those being here, you have this really large bulbous horn coming off the back. You can hopefully see the nose, right? Looking at the face, on top, below, and the side of the head. And this is Zea pelta. This was more recently kind of discovered and named. But what also ends up happening because of this is oftentimes we're only getting a single specimen of each of these things. We don't have multiple examples yet of most of these things as they are being named. As I mentioned earlier, well, we'll do that in a second, I suppose. We have Glyptodon pelta, a nodosaurid, an ankylosaur without a tail club, essentially, named mainly from osteoderms, bones within the skin that covered this animal completely. We do have at least a little bit of other material that hasn't really been fully described. Things like part of the dentary, right, the lower jaw, and part of the supraorbital, the bone around the eye itself. But mostly we know this animal from different osteoderms that were covering it.
So
Yes.
how do you make that sketch then? How
So
do you know what the legs look like?
sure. So basically what we end up doing, right, is that if we were going to look at this, all we could really then draw is exactly what we have, right? But we end up having a lot of animals that are related. And depending on how closely they're related, you can determine how close these things are. And if you have more complete animals elsewhere that are very similar, the idea is, while it's hypothetical, you're going off of what you know from those other animals. So what this ends up being is very close to a dinosaur called Sauropelta. We have basically all of Sauropelta. So we know what Sauropelta looked like, and we know then roughly then what this animal is going to look like. We can always determine by finding more material that it's not even close. And there's lots of weird things, and then we can figure out we were completely wrong. And that has happened certainly in the past with some dinosaurs, but mostly we are getting a lot better with understanding how close things are related and then how they'll actually be. So in a similar way with something like this, where we lead into a couple more problems, I had mentioned Achislopelta earlier because it had been described by Mike Burns, who had come to school here. And it is known by osteoderm, and it's known by some of the postcrania. This is a part of the scapula coracoid, right? The shoulder blade, essentially. We have some of the limb bones from this as well. But while this was originally described as an ankylosaurid with a tail club, it was then looked at again and thought to be a nodosaurid, something like this without a tail club. Much larger spikes potentially on it, a different head with less armor plating and things like that. Since then, I have seen multiple studies going back and forth as to which side this is actually falling on, right? So we know it's an ankylosaur. Whether it's part of the ankylosaurid or nodosaurid group, we actually still don't know yet. So we still need more material to fully really flesh that out and understand what's happening. We move on to hadrosaurids, those duck-billed dinosaurs. Remember I talked about Cretaceous being that early one that had been named. Here we have things like, this looks like a blob, but it's Anasazisaurus. This is oftentimes what you get when the skulls become disarticulated. There's an eye here, or the top of the skull here. This is the nose portion coming down. This is part of a lower jaw that's kind of been shifted up as it was preserved. And so this kind of is showing that, even though a lot of those won't make much sense, but you have things like the nasal, the jugal, right, the cheek, things like that coming out through. And what you get is an animal looking very, very similar to this, basically. Now, this is basically what ends up being a very simplified look. If we look at another one, Shobitosaurus ostromi, this is the animal itself. You can see the eye here again, the top of the nose. This part's missing, the back of the head. This is it reconstructed similar to other animals that similar to basically. This portion of the skull is what's actually preserved. These smooth portions are all reconstructions for what we think it would have been like. What ends up happening is that it looks very similar to the last one. And if you remember, it actually looks very similar to Cretaceous. There's been discussion that all three of these are the same thing. And maybe they are. Sometimes it's very difficult when you only have a few specimens to know what the range of variation is with a lot of these dinosaurs. And so it's hard to say how much variation is one species versus multiple species. Additionally, without getting too much into the weeds, the idea of what a species is today for modern animals versus what a fossil species is distinctly different. And it pretty much has to be different because we only, especially when we're looking at vertebrates, are really looking at the bones. But we're normally only looking at the hard parts of these creatures anyway, in some form. So it's going to vary. So there's still a lot of discussion as far as what the difference is between these, and only having a single specimen of each makes it difficult to really have a good handle on that. The hope is that we keep getting more specimens and we get better information based off of that. Additionally, we have things that we still don't have enough material. We know they're new or distinct, but we don't know what they are. Things like this, which is Hypacrosaurus-like. The lambeosaurs are those duck-billed dinosaurs, oftentimes with crests or things on their heads. When you think of Parasaurolophus, that's what you're thinking about. Hypacrosaurus was one of these dinosaurs. We know based off of features here, we have a jugal, cheek, humerus, upper arm bone, that it fits within this group. We also know it is very similar to Hypacrosaurus from Montana and Alberta, but seemingly different. We just don't have enough material. So again, we still need to keep going out there, collecting more material to figure out how it actually falls in place compared to those. But sometimes we do get more material. It just doesn't happen often. So I talked about Parasaurolophus before with Tubicin and Pseudocristatus. And what we have is that while we had those specimens collected really early, more recently we've had better specimens collected. Here we have Tubicin, and before we had the very end of that crest, now we have the majority of the back of its head, the eye is here. We have the majority of the crest here. And that was collected early on in these 90s when we were first doing that collecting. Even more recently, over the last 2 years, I believe, we have another crest of Pseudocristatus, that other shorter crested animal. And here you can see those comparisons. Now, the idea before potentially was that they were potentially males and females of the same species. Stratigraphically, right, the layers the rocks are found in are actually slightly different. So that suggests maybe it wasn't the case. And now that we've gotten new specimens of both, we can tell that the way those crests are formed, the bones that create them are very much different. So we know they're not males and females of the same species, if not sexual dimorphism.
I guess my question is a variation on Marcus's. I'm guessing that you have specimens from elsewhere that put the rest of the critter together because
Yes.
the white areas in there, the crest there, pretty small part of the whole critter.
Yes, certainly. So what we end up having, right, is that we just combine these and we compare these with animals like Parasaurus walkeri from Alberta. Then we know of what the whole animal is then looking like.
And that you know are similar.
Yes, yeah, because even walkeri has a similar crest to this. It ends up being a bit smaller, not quite as rounded or bulbous, but it's essentially the exact same. Otherwise, it's a very, very similar skull. And postcranially, we end up finding out that most of the things behind the skull on these are relatively conservative. There's not a lot of change or variation as we go through these animals when you're looking at large scale groups. So these are like the lambeosaurs. Lambeosaurs all have very, very similar body plans, essentially.
If Mark Twain saw this, he would probably say something he said about some other subject. What a marvelous amount of conjecture one can get out of such a trifling investment of fact.
I would certainly agree.
Oh,
Sometimes the amount that you go beyond is a little bit too extreme. Now, most of the time when we write these up, right, we do a lot better at just sticking with what we have and saying what that actually is. But when we try to expand that to give people a better idea of what these things were on a more full scale, then yes, then it leads to a lot more conjecture. Now it's conjecture based off of facts we know or other information we're using, but it's still conjecture. All right. So as we run through these other things, we'll just go real quick with the idea that even when you look at things like other hadrosaurs, rather than understanding new species, biodiversity, differences and things like that, we do get extra information from these. And so we also get ideas of how they are changing through ontogeny, how they age, how they get bigger, right, as they get older, and what that's basically showing. So we get things like this juvenile, this is actually a hatchling humerus, which is, roughly 2 inches long, meaning that the whole animal has been incredibly small, especially compared to these adults. But we know that this ends up being one of these juvenile lambeosaurs, these crested hadrosaurs. We also get other material, things like we have skull pieces from another juvenile lambeosaur. This includes lower jaw, pieces of the skull itself. And what this basically ends up showing us are that we can see how these animals are changing and aging through time, at least morphologically, on a relatively coarse scale, and how these things then go from something small and cat size oftentimes to something that ends up being 20, 30, sometimes 40 feet long. So if we move on to ceratopsids rather quickly, right? We have things like Ohoceratops. Again, here we have multiple individuals. You get things like the back portion of these horned dinosaurs, the frill, you get portions of the horn, at least the nasal horn, lower jaws. And we get an idea for things like this, that this is very similar to what we know as Triceratops from further north, based off of all the pieces we have. So we get an idea then of how these things are going to look on a more large scale basis. Yes.
For the colors in the picture, is that completely guessing or is there any?
For the most part, yes, but not necessarily completely. We are getting more and more information for dinosaur coloration as we go. Currently, feathers are a little bit easier to get colors for, but really that's only certain colors, mostly black, brown, and red, because of the melanosomes that you get from them, but you can get patterns. We've got skin patterns for other animals that we're getting a better example of. There's an ankylosaur found in Alberta, where we at least understand that there was counter shading going on. Basically, it was really, really light on the bottom and dark on top, and you get counter shading occurring that way. And we're getting at least some as far as color patterns for others. There was a hadrosaur that has full color patterns present from Montana as well, where you can see that there is striping, almost like zebra striping, around the back portion, around the hips, and the front part of the tail. The rest of it was a little bit darker, and then the front portion ended up being lighter in color. So exact colors, guesswork for the most part, based off of birds and reptiles, but patterns oftentimes at least a little bit more information for that.
Are you guys getting any better at sketching any fat or excess skin that wouldn't show
Yes.
up on bones?
So we're getting a lot better with understanding the extreme limits of where that's going to be. Some of that ends up dealing with things. There's a lot of work being done right now on tendons, the way these bones are being held together within the limbs themselves, and to a point through the actual spine and the head, which is giving us a better idea of what the more extreme limits of these are. You'll see some pictures where there's still some where we don't have a good handle on that. Things like the really large animals like sauropods, it's hard to say how much excess fat you're going to have on that versus how close it's going to lie to, say, the bones themselves. So we get some idea of some of those things, but some of it is still using, again, what we see from oftentimes larger mammals today to get an idea. So we use things like elephants and rhinos as large-scale terrestrial animals to get an idea of what we're looking at. So as we run through these, then we get things like Titanoceratops. Again, this is a dinosaur, other horned dinosaur. A lot of this ends up being conjecture as well. This has been claimed to have the largest terrestrial vertebrate skull of anything ever, just under 9 feet long. So absolutely huge. But when you look at this, there's been a lot of debate as how accurate that may or may not be, because what you end up having is this white portion is preserved. So this ends up being conjecture based off of the dimensions of this portion of the frill as it goes up. So how accurate is that? I would say probably not very. But currently it's still claimed to be the largest vertebrate skull. Now, even if this is not 9 feet, this is still probably a very, very large skull regardless, and probably close to, at least terrestrial wise, the largest skull we actually do have. So rather quickly, we get things like other ceratopsids. We end up seeing there's a lot more variety than we thought. More recently, things like Navajoceratops, Terminocavus. Again, skulls that look rather similar. Differences end up being in things like, right, how closed off these top portions of these frills are, or things like Bisiceratops, more recently named with things like a more elongate frontal portion of this. There's other aspects of the bones we won't get into, but still, we know that we have a larger variety of these guys. And one of the things we want to then see as we go through that is how this compares over time. If we look at, again, we're focusing here on the south. If we look at these dinosaurs, we have several ceratopsids, these horned dinosaurs from New Mexico, things like Ohoceratops and Titanoceratops, which ends up being, Oho ends up being here, Titano ends up being here. Red, in this instance, is referring to things from southern United States, blue is north. This is showing relationships. We have things like Sierra Ceratops over here being in among a lot of other red ceratopsids, again, all things from the south. You have things like Bisiceratops and Pentaceratops, again, being things in the south. All I really want you to kind of look at and get an idea here is that while there are some portions where animals that are closely related are all from the same region, there's a lot of other areas where this is not occurring, right? You have things like here where you're getting blues and reds together. This is just showing these animals are probably moving north and south quite a bit, right? There's probably quite a bit of movement occurring migrationally between these, allowing you to get these closely related animals in different geographic regions over time. So, as we quickly go through some other ones, things like Pachycephalosaurids, these dome-headed dinosaurs, we get things like Sciraptolus and things like Stegosaurus, right? These other smaller dome-headed dinosaurs. Here we get a little bit more information of these as well. Things where we can look at the internal structure of these domes, get an idea of how old these are individually. This basically showing that these are slowing down, almost stopping with growth. So they're very small individual dome-headed dinosaurs compared to a lot of the other ones, which end up being closer to our size, basically. Well, again, if we look at things like this, we get an idea of Ceratolus being down here with some other animals from the north. We get Stegosaurus being a little bit further up here, showing not as clean a variation, but still a lot of connections with more northern animals. So again, we're getting this idea that these animals are moving north and south on a more significant basis. Again, I mentioned sauropods like Alamosaurus. And since we do have more information about this, things like cervical vertebrae, again, vertebrae from the neck itself of this animal, including things like this partial femur, show that this animal ends up being on scale with the largest sauropods we know about from anywhere. So you're looking at these things that are dozens of tons, and you're also looking at animals that are, in the 90+ foot long range. These sauropods end up being the biggest terrestrial animals we have. Things like Puertosaurus and Argentinosaurus from South America end up giving us a better idea. Now, the overall weight of these animals is heavily debated. And again, part of that is the idea of what we know about the soft tissue structure of them and how that's going to work. So there's lots of variation on how we try to calculate what those sizes are. Regardless, we know that they were incredibly large. You're looking at things that are like on the size range of a herd of elephants is equivalent to one single individual, basically. Right? We quickly look at theropods, those meat-eating dinosaurs. We get things collected more recently, like this idea of Ursa. Again, Seeley, one collected by Paul Seeley, or at least found by Paul Seeley. But one of those Tyrannosaurids, a bit smaller than T-Rex, but still the same family, these large things. You can see the eye ends up being back here, large teeth, lower jaw, right? And we can see then where these things lie. If we look at other ones, we end up getting large theropods similar to T-Rex. Right here, we have material that is very similar to what we know of as T-Rex. This ends up being a staphylocoracoid, again, part of the shoulder. You look at right here. And we know that this is very similar to T-Rex. It's from the south. It's not T-Rex. It's something new or distinct or different. We just don't have enough material of it. It ends up being a little bit shorter in size, but probably a little bit more robust than what we think of as T-Rex, based off of what's happening with the shoulder and forearm of this animal. We get other theropods, those ostrich-like dinosaurs, here being a ornithomimid-like ornithomimid. Again, not enough material to know exactly what it is. We just know that it's ornithomimid-like. We have other ones, things like Penignathids. These are more parrot-like dinosaurs. Again, probably basically no teeth on almost any of them, especially the later ones that we know about. Going to be covered in feathers. We've shown that they basically all have some kind of crest on them, reduced jaws. So exactly what they were eating, it's hard to say, but whatever they were eating, they were not chewing it up. Other theropods, things like Troodontids, these are more famous for being potentially some of the smartest dinosaurs based off of brain cavity size. They would have had relatively small teeth. That would have been slightly serrated. We have mostly just tooth material from these things. We know they were there, a little bit of skull material, knowing they were present, but not much else. Then we get to the dromaeosaurids, those raptor dinosaurs that are similar to and related to Velociraptor that we're at least a little bit more aware of, right? You get things like Sornitholestes sullivani, one that was named after Bob Sullivan, named partially for having an enlarged portion. This is the underside of the frontal portion of the top of the skull up here. That portion that is highlighted is the olfactory bulb surface. It's suggestive of the size of the olfactory bulb within the brain, which is indicative of the sense of smell of these animals. But this having a much larger olfactory bulb surface, it suggests this animal had a much better sense of smell than other animals that we would potentially be looking at within the same basic group. More recently, I worked on and described Dinobellator. This is another dromaeosaurid from later on. Basically, this is all one individual with various bones throughout the actual skeleton that was basically associated. The bones were together but not articulated, not connected directly as they should have been in life. So oftentimes when you're looking at some of these things, you're getting situations like this. It ends up being found here. And what you end up seeing are things like this. If we get in a little bit closer, you might get to see this is a lot of random bone chunks. Lots of chunks all over the place. At least he is pointing at something that's a little bit more clear, which is a manual ungle, essentially a hand claw for this individual. One of the ways to know exactly what it was early on. So going through this rather quickly, looking at this animal, looking at what we know about it, you get things like the humerus. Again, you can see that the humerus is incomplete, which is why some of that's dashed. But you get key areas for muscle attachment. One of the keys for an animal like this that helps us understand why these animals can be different are looking at different pieces of this. Basically, this is called the deltopectoral crest of the humerus. It's important for muscle attachment. One of the key areas for this is this portion over here, part of that blade, that crest, that ends up being an attachment area for the brachialis muscle. The brachialis muscle is for flexion of the forearm, which meant that this animal had a much better flexion for its forearm and its forelimbs than other animals would have that were related to it. We also have things like the ulna, right? This lower portion of the bone. For these dinosaurs, that's important because what it ends up showing is ulnar papillae or quill knobs. These ends up basically being attachment points for large feathers on the forelimbs of these animals. While we already assumed that these had basically feathers on their forelimbs, just like Velociraptor would have had feathers on its forelimbs. This shows, again, another example confirming that this is present in other individuals within the same group, suggesting that it's not a one-off of one individual. It's present throughout it, basically. We also get key areas like caudal vertebrae, this being an anterior caudal vertebrae, probably the first caudal vertebrae in the tail itself. A key aspect of this is that what it ends up showing for the attachment surfaces is there's a lot more movement within this caudal vertebrae than any of the others within the group we've seen. Now, why might that be important? Well, these dinosaurs themselves have tendons and elongate bone attachments throughout the tail itself, really stiffening up the tail, basically to act as a rudder. So basically the idea is that the tail would be held straight behind it. This animal would have been fastly running and it would have used that to help balance itself. So if we take that tail and we allow more movement at the base of that tail for these vertebrae, what you end up getting is a larger range of motion for the entire tail itself, especially if the tail is held stiff as a rudder. And so what you end up getting is that these animals can end up using that tail as a counterbalance when they're actually hunting things and in full predation mode trying to actually attack something, right? So what you end up getting is that this animal ends up being a lot better for active predation at things because it's got the ability to use that tail better as a counterbalance than other members of the group. And so we also have things like claws, which we won't get into much here, but this dinosaur also has a lot of things that are not quite normal with it. Things like this point here, which ends up being basically what's probably a compressionary point. Now, whether that's pathologic or not is hard to say, but we do have ribs as well that are pathologic. They show abnormal bone growth, which also means this animal survived with injuries that were then able to grow as those bones move forward. We have a lot of other pathologies in general that we see when we look at these things. Things like this being a pathologic growth on the hips of ceratopsid, really weird bone growth. As far as this bone coming up, flaring out over top the hips of this animal due to some kind of injury. Other pathologies like compression fractures within bones, this being one of those ostrich dinosaurs, right? Showing active running, but then being able to survive with these injuries. We also have things like bite marks. This is on the humerus upper arm bone of a hadrosaur. Those bite marks are in agreement with teeth the size of tyrannosaurids. In addition, we have other things such as this. This is a scapula and what ends up being several vertebrae with stomach content. Chances are this is a regurgitolite of a tyrannosaur. The only thing that can eat something this size is going to be a tyrannosaur. A regurgitolite, again, being something that it regurgitates. Basically, here is a small hadrosaur that was probably eaten by a tyrannosaur, partially digested, and then thrown up again there afterwards, leaving what we get of as this material afterwards. So, real quick here at the very end, all I'm going to mention is the idea that when we're looking at these animals from the south and we're looking at all these dinosaurs in this variation, one of the big things we want to understand is how this fits into a slightly larger picture. So here at the end, when we compare things like the north and south in the late Cretaceous, what we end up getting is that we get different faunas, different groupings of dinosaurs present in different areas. Now, these have oftentimes been called things like the Triceratops community and the Alamosaurus community, right? So we get the sauropod things from the south. We don't get them in the north. There is a demarcation, a deconnection there around Colorado, basically. And they've looked at this in many ways, comparing, say, types of these horned dinosaurs and determining that you're getting different horned dinosaurs everywhere. No matter where you look, you're getting a distinct variety. And the idea then is that endemism, right, the idea of individual or distinct faunas or groupings of animals are present all over the place in every different area you're looking. So why might that be? Well, part of what we end up seeing is that when we look at the north versus the south, while we get differences, most of the major groups are still there. So while species are different, maybe genera are different, actual overall groupings, say families, larger clade size, are going to be the same for the most part, no matter where you're at, although there'll be difference in how common or uncommon they are. So we'll end up seeing, when you're looking at things like from the north here, you'll see horned dinosaurs, ankylosaurs, small theropods in both places. You'll see large hadrosaurs. You'll see these gigantic theropods present in both places. The one big key difference you end up having here, right, is this guy. Those sauropods being present in the south versus not in the north are making a key distinction between what's happening between these two areas. And we still don't really completely understand why they're only getting so far. We have sauropods in South America at this time, and we've had them for all the time before this. So some thought is that they're coming up from South America, and for some reason, they can't get past Colorado, which already doesn't make sense when we think about the idea that we showed other dinosaurs that are present in the north and south with no real problems, presumably moving up and down this portion of the country or the continent. So there's something else potentially going on that's causing these animals not to go beyond that. Some thought was that you had things like T-Rex to the north that were not causing that. But clearly, we have large theropods the same size in the south as well. So it's not T-Rex deterring these sauropods from getting further up. Something else is clearly going on. Now, part of the issue we end up running into is simply the idea that there is not quite complete agreement in exactly when these things are occurring. Right? If you look at these, while there is overlap, not all of these faunas are happening at the exact same time. And so I think one of the things that we have to bear in mind is that you have to look and see where these fossils are coming from, and if they are in agreement the exact same time-wise as to when these other things are occurring. That's the only way we're really going to have a good handle on how they're actually comparing. Because if things are 1 or 2 million years apart, which is relatively easy when you're looking at scales of this size, you can run into extra issues and problems when you're trying to compare things. And if you're trying to compare apples with oranges, you're not going to necessarily make that work, right? So I will leave that there. If you have any questions, I will be happy to answer them.
You mentioned something about some of the flora
Yes.
that you guys have come across. Can you comment about, so there's clearly some sort of difference between
Yes.
the north and south. Do the flora give you any idea as to any sort of climatic differences between those two regions?
So what we're really getting mainly, the only time we're getting a major floral change seemingly at this point in time is if we're changing elevation a bit more. For the most part, we're not having enough change in the climate or the temperature during those two areas to get significantly different flora. So for the most part, even though we don't have as much of it, when we're looking at areas in Montana, in southern Canada, especially southern Alberta, we're essentially getting the same flora showing up in both areas, at least the same major groupings of flora, right? So it doesn't seem to be a difference in food availability. Otherwise, you might be able to say that things like Alamosaurus prefer some kind of flora, right, that they would focus on that might allow them not to go up there and cause differences in that. But we're not seeing any of that happening, at least from what I can tell.
When you're spending 5 field seasons to extract a skeleton,
Mhm.
does that mean you're leaving skeletal elements out there for 5 years? Or are you taking out one piece and then going back another summer, taking out another piece?
So it all depends on exactly what we're trying to get out and how we're trying to get that out. If we do one large jacket, which has happened, it might stay out there for a while. There are also
How do
times
you protect it?
you put a field jacket on it and you allow that field jacket to stay out there. Sometimes what that means is you put a field jacket on it, you coat it, you PVA it, you cover it up in tarp and things like that to try to protect it, then you rebury it basically. And then you come back to that same spot in the following year with the hope that it's still going to be okay. Most of the time, if we think something's not going to be okay, we will do everything we can to try to make sure we get it out. So it doesn't say there over winter and then spring before we get back out the next summer. But it does happen depending on the size of what you're looking at.
Any other questions? All right, thank you, Stephen. So do you have like a lifetime of material that needs to be prepared?
If they lost,